We've looked at the behavior of gases. Now we'll consider the physical properties of liquids and solids and the phase changes that occur between the states. Virtually all substances that are liquids at room temperature are molecular. And understanding the attractions between those molecules, or intermolecular attractions, is necessary if we're to understand why molecules have a particular shape, or the energy needed to break the bonds in a molecule, its bond energy, or why molecules have a particular chemical properties. Let's start by reviewing some general properties of solids, liquids, and gases. As we learned in the previous chapter, the average kinetic energy of gases is proportional to absolute temperature. Gas molecules are constantly moving. Since there's very little attractive force between the gas molecules, they're going to move randomly and they're going to expand to fill their container. Liquid molecules are somewhat more attractive. Molecules of a liquid are held closely together, but the attraction's not so strong that they can't slide past one another. And so liquids can be poured and they take the shape of their container. In solids, the intermolecular attractions are strong, so molecules are essentially locked in place. Although they are vibrating in place, they aren't very compressible because there's no room to squish the molecules together anymore. Many solid substances are composed of molecules that are highly ordered in a regular pattern. We call them crystalline. Quartz, or silicon dioxide, is an example of a crystalline solid with a very ordered, regular pattern. Or it can have an amorphous structure, as in glass. Whether a substance is a solid, a liquid, or a gas depends on two things: the kinetic energy between the particles and the strength of the attraction between those particles. Remember that kinetic energy depends on temperature, keeping those particles in motion. But the intermolecular attractions pull the particles together. Gases at room temperature have the weakest intermolecular attractions, and solids have the strongest. We can change that by changing the temperature. If you consider that solid H2O is ice, if we heat it up, increasing its kinetic energy, the molecules can now move past each other, and so we have a liquid which we can pour. And if we keep increasing the temperature and increasing the kinetic energy, then the attractive forces weaken even further, and those molecules then go into the gaseous stage or form steam. Remember from the last chapter that the pressure of a gas is inversely proportional to temperature. So if we increase the pressure on a gas, the temperature will decrease. Propane is a gas at room temperature, but a liquid in this tank because it's stored under higher pressure. Before we get into the types of intermolecular attractions, remember that the covalent bond, for example, the one between this hydrogen and this chlorine atom, is strong because chlorine is so much more electronegative than hydrogen is. The force that's pulling these two molecules together, the intermolecular attraction, is weak in comparison to the covalent bond that is connecting the hydrogen to the chlorine. So then we could safely say that all intermolecular forces are weak when we compare them to the bond that's holding the molecule or the ionic compound together. Having said that, intermolecular forces are responsible for a lot of properties of liquids, like boiling point. Liquids have to overcome the attractive forces in order to move apart and form a vapor. Water has really strong intermolecular attractions. It takes a lot of energy to overcome those attractions. The boiling point of water is 100 degrees Celsius. But if we compare that to hydrogen chloride, whose intermolecular attractions are really weak. There are 4 types of intermolecular forces: London dispersion, dipole-dipole, and hydrogen bonds. And these are known collectively as van der Waals forces. It may exist between neutral molecules as opposed to ions. And the 4th type is the ion dipole. And these exist between an ion and the end of a polar molecule. Polar molecules are dipoles. They have a positive end and a negative end because of the differences in the electronegativities of the atoms involved, in this case the oxygen and the hydrogen. When we put an ionic compound like sodium chloride into water, the negatively charged chloride ion is attracted to the positive end of the water molecule, the hydrogen end, and the positively charged sodium ion is going to be attracted to the negative oxygen end of the water molecule. And so we have an intermolecular attraction known as an ion dipole. The other 3 types of intermolecular attractions that we refer to as van der Waals forces all occur with neutral molecules. And remember, when we say molecules, we're referring to covalently bonded compounds. And the first of these is the dipole-dipole. And this is what attracts neutral polar molecules to each other. The positive end of one molecule is attracted to the negative end of the next. But these forces are only going to come into play when the molecules are close enough together. If we look at liquids with similar molecular weights, we find that the greater the dipole moment, the stronger the attraction. In other words, the higher the boiling point is going to be, because more energy is going to be required to overcome those strong attractions. The second type of van der Waals forces that we'll look at are called London dispersion forces. Oxygen molecules are nonpolar. And then we know gases have very little attractive forces, but they must have some degree of attraction since we can liquefy them. The attraction is believed to be formed by the movement of electrons as they move around the atom, creating temporary dipoles, temporary momentary dipoles. Larger molecules do this more easily. Their large electron clouds create a squashiness where the distribution of electrons gets moved around, creating these dipoles. We call this polarizability. So then, the bigger the molecule, the stronger dispersion forces. And all molecules, polar or nonpolar, have dispersion forces. The shape of a molecule also helps us to determine how strong the attractions will be. Although these 2 molecules both have the same molecular formula, the N-pentane has got a higher boiling point. Because of the shape of the molecule, its molecules, because they're longer, are more in contact with each other, thereby increasing the amount of intermolecular attraction, and therefore the higher boiling point. The third type of intermolecular force, a very strong force, is the hydrogen bond. The hydrogen bond is a very special intermolecular attraction between hydrogen in a polar bond, usually connected to fluorine, oxygen, or nitrogen, and the unshared pair of electrons from another atom, which will usually be also bonded to fluorine, oxygen, or nitrogen, the 3 most electronegative elements on the table. Here we have hydrogen bonding in water molecules. The hydrogen end of one molecule attracted to the unshared pair of electrons on the oxygen of the next water molecule. Here we have hydrogen bonding between hydrogen from the water molecule to a fluoride ion. Here we have it attracted to the unshared pair of electrons on ammonia, on the nitrogen of an ammonia molecule. And Finally, the hydrogen of one molecule to the fluorine end of another in hydrogen fluoride. And here you can see that we have ammonia and water, two different types of molecules, and a hydrogen bond forming between the hydrogen end of one and the unshared pair of electrons on the other. Here we have a graph that's showing us boiling points versus molecular mass. And if you'll notice that the molecular mass of methane, CH4, and water, H2O, are pretty close to each other. But the boiling points are hugely different. And the reason for this is that CH4 methane is a nonpolar molecule with just London dispersion, very weak London dispersion forces holding it together. And so very little energy is required to separate those molecules and allow them to form a gas. Compare that to water, which has really, really strong hydrogen bonding. And since the intermolecular attractions for water are so strong, it's going to require a lot of energy in order to allow liquid water to vaporize.